Recall from section 2.3 that S of t was defined to be the position function. So this is where the object is located at some time t. And we defined the velocity function to be v of t. Now, this is how fast the object is moving at some point in time, right? It's the change in the position. It's the first derivative of the position function. So if I take the derivative of the position function, then I get the velocity v of t. And then the acceleration function, this is how the velocity is changing. So the acceleration is equal to the derivative with respect to time of the velocity function. But since the velocity function is the derivative with respect to time of the position, then to get the acceleration in terms of position, I take the derivative of the position twice. Okay, so what do we know? The integral is the opposite of the derivative. So if I have s of t and I take the derivative, I get down to v of t. And if I take the derivative of that, then I get down to a of t. Okay, so t each time, right? So the only way to go back the opposite way would be to integrate the acceleration to get to velocity, and to integrate the velocity to get to position. So I'm going to integrate the velocity function, and whenever I integrate the velocity function, what that does is that gives me the position function plus c. Now, to go one step further, if I take the integral of the acceleration, I should get my position function, right? Because if you think about it, the derivative of the derivative gets you acceleration. So if I take the second derivative of the position, I get acceleration. So it would make sense that if I do two integrals of acceleration, then I should get the position function, right? Now, in order to do this, the integral of acceleration is what? It's the it's equal to the velocity function. But remember, the velocity function is just like this right here. If I integrate velocity, I get position plus c, right? So if I integrate acceleration, what do I get? I get velocity plus c. Okay, so that's all this is saying here is that a of t dt is equal to v of t plus c naught. Now I'm going to put a c naught here because I have different c's going on, okay? So now I want to integrate that inside. So I just integrated this here, and that took off one of the integrals, but I still have another integral left, right? So now I need to integrate this function. Well, the integral of v of t is equal to s of t plus c, right? So I'm going to call this c naught, okay? This c naught here has a t. Remember, if I have the integral of some constant dt, or I think the rule said dx, then this is equal to cx plus some c, right? Where it's like a different c, okay? So if I take the integral of 5 dx, that just gets me 5x plus c, okay? So with this one, that's where that t came into play. And then I also have the plus c that I had going on here from integrating this part right there, okay? So not only do I need info about the velocity, I also need info about the position. I need initial value information in terms of the velocity function. I need some initial value. And then in terms of the position function, I need an initial value. If I'm going to use the second derivative of acceleration, right, I'm going to use this second derivative of the position, which is acceleration rather, I need to also have information about the velocity initial position and the position's initial position. Okay, so these initial values are particularly important to get that particular solution for the position function s of t. So let's do an example, and I'm going to show you what I mean here, okay? If I'm given the second derivative, remember, second derivative of a position function gets me acceleration, right? So this x squared represents my acceleration. I want to find the original position function f of x, but I'm given f double prime of x. So how do I do this? Well, I need to figure out a way to use the information here, which is that information that I needed, right? Check, check, okay? In order to get f of x. So how do I know f of x is related to f prime prime? If I take the integral of f prime, I should get f, right? So I need to integrate this thing twice. So let's do that. So the first derivative, okay, the first derivative is equal to the integral of the second derivative. So integrating cancels out derivatives, right? So an integral will cancel out this to get me just one derivative. And then if I want to get rid of that one derivative, I just integrate again and I'll get f. So that's what we're doing there. We're using integrals to cancel out the derivatives. Okay, so what is the second derivative? Well, the second derivative is x squared, so I'm going to replace this with x squared. And now I'm going to integrate. Integrate, power rule, add 1 to 2, I get x to the 3, divide by it, and then plus my c. And I'm going to call this C1. Very common to do stuff like this, to label it, especially when you have multiple derivatives going on here. I'm going to use more than one c, so I'll label this C1 so that I can distinguish between the different c's. Now this becomes an initial value problem, because what do I have? I have f prime of x equals x cubed over 3 plus c1, but what do I know? F prime of 0 equals 6. That information I'm going to use here. I'm going to plug in 0 everywhere I see an x and solve for c1. So let's do that. I plug in 0. It looks like this here. Now what do I know? F prime of 0 is equal to 6. So I'm going to replace that with 6. And then 0 over 3 is 0. And so c1 equals 6. So I'm going to come in here and replace c1 with 6. And so that tells me the derivative is equal to x cubed over 3 plus 6. Okay? Now that I have the derivative, I'm going to use the derivative and integration to get the f function. Okay? So f of x is equal to the integral of f prime of x, right? We've talked about that. The integral undoes the derivative, okay? So they are inverses of each other, inverse operations. So this and this cancel each other, basically. I get f of x, and that's what I'm looking for. I'm looking for f of x. So what is f prime of x equal to? F prime of x is equal to x cubed over 3 plus 6. So now I need to integrate this. The integral here, I raise this to the 4th power and then divide by 4. Dividing by 4 gets me 3 times 4 is 12 in the denominator. Integrating 6 gets me 6x. Now I add a plus c, but I don't put c, I put c2 because I already had a c1 there. I'm trying to tell the difference between the two. So what do I have? I have f of x equals this thing right here, okay? But what do I know? I want to know the particular solution for one fixed f of x value. I don't want some arbitrary c2 here. So in order to figure out what c2 is, I use the initial value information here, where everywhere I plug in x, I'm going to replace that with a -1 here, okay? So I put a -1 in there, and what do I get? Well, f of -1 is equal to 13 over 12, so that's 13 over 12. And then whenever I do this math here, I get 1/12. When I do that math here, I get -6, and then plus C2. So if I combine all this together, I guess that's going to get me 13 over 12 minus 1/12 plus 6 equals C2. This is going to get me 12 over 12, which is 1. So 1 plus 6 is 7. So that gets me a C2, whenever I simplify, of 7. And so what do? I replace this C2 with 7. Okay, so f of x is equal to x to the 4th over 12 plus 6x minus, or plus rather, 7 there. Okay? So I want to zoom out so that you can kind of see everything in one shot there. And hopefully you get the big picture of what's going on here. All right, so just to recap, if I'm starting with a position function, I take the derivative of the position, I get velocity. If I take the derivative of the position, I get the derivative of the velocity, which is acceleration. So going the opposite way, if I integrate the velocity, I get the position plus c. If I integrate the acceleration of the acceleration integrated, then I get the integral of the velocity, which the integral of the velocity is the position. And so in general, this is the format of the general case right here. And you saw how we ended up here with this linear term right here, and then the constant. We got that linear term here, and we got that constant there, okay? So truly, like this piece right here, this was the piece that was found straight from that right there. If we go back, x squared, if I just integrate this, I get x cubed over 3. Integrate again, I get x to the 4th over 12. That piece right there goes to right there. And so really what it amounts to finding is what this C0 and C1 is, which that is found by the information of the position and the velocity information right here from those initial value problems. Okay, so this is like two initial value problems in one. Okay?